So for FRQ number 4, it gives us that a point P mass collides with the rod, and it wants us to work with the momentum. So the information that initially gives us is that mass of the point P is equal to m2, and mass of the rod is equal to m1, and then inertia of the rod is equal to m1 L squared over 12. And then it also tells us that when point P initially hits the rod, its initial velocity is v, and then when it bounces back off the rod, its final velocity is negative v over 2. So with that information, we'll go to part A, where it asks us to use principles of conservation of momentum to find the final velocity, linear velocity of the rod. So we know that momentum initial equals momentum final, and momentum can be broken down into mass times velocity. So we have the only momentum initially comes from mass P because it's the only thing moving. So MP times VP initial equals, now there's going to be a momentum for mass P and for the rod, so it's going to be MP times VP final plus mass of the rod MR times VR final, and VR final is what we're trying to find here. So if we plug in what we know, MP is M2, it'll be M2V equals M2 V over squared, and we'll add the negative for the V over squared at the beginning here, and then plus M1, and then VR, velocity of the rod final, is given as V prime. So we're going to combine this term here on this side to this side. We'll move it over since they have the same variables, and we're also going to divide both sides by M1. So we move both terms over, we'll have that M2V plus M2V over 2, all divided by M1 will equal V prime. So we simplify this up here. At the top we'll have we'll have 3 over 2 M2V, because 1 over 1 plus 1/2 is 3 over 2. And then at the bottom, we still have this M1 here. So that gives us this should be a prime. That gives us the final velocity, linear velocity of the rod. And then for part B, now we're going to use angular momentum conservation to find, the final angular velocity of the rod. So angular momentum initial equals angular momentum final. And there's a couple more definitions we need. So angular momentum is broken down into moment of inertia times angular velocity, and this varies depending on which object you're looking at. So for point P, its moment of inertia is m2 rp squared. And we actually don't know what RP is because it isn't given, but we can quickly find it by looking at the rod. So R is the distance that the point P hits from the center of the rod. So the center of the rod to the end of the rod is L over 2, and it hits here, and we're actually given this distance here is L over 6. So to find R, which is this distance in the middle, we'll do L over 2 minus L over 6, which gives us L over 3. And that is going to give us RP. So besides that, we already know that moment inertia of the rod is m1 L squared over 12. So with that information, we can continue to work. So breaking this down, the conservation of momentum, angular momentum, we have that the moment of inertia for P following this step here times angular velocity P initial equals a moment of inertia P times angular velocity of P final plus moment of inertia of the rod times angular velocity of the rod final. And this is because only point P is moving initially, while at the end, both point P and the rod have a momentum. So we know that IP, we can break that down to be M2 RP squared. And oh, I also forgot to mention that whenever we're looking at angular velocity, if we need to, we can break it down to V over R. And this, of course, will correspond to whichever velocity and object we're looking at. So if we're looking at if we're looking at the angular velocity of P initial, we're gonna want to have the velocity of P initial on top, and then the R of P on the bottom. And then we're going to do the same for IP and angular velocity P final. So we have M2 RP squared times, this time it's going to be VP final over RP. And then again, we know that the moment of inertia of the rod is given as M1L squared over R times angular velocity of the rod final, which is what we're looking for. And plugging in everything we know here, this time we have we're actually going to go ahead and cancel some stuff to make it easier. So we can cancel out the RP's at the bottom here and this exponent RP. Same for this over here. So we have M2 RP. We already found up here to be L over 3. So sorry, not yet. So M2, we'll write it as 1/3 L to make it easier later when we're simplifying. And VPI, we already know also is given as V equals M2, again RP is 1/3 L. VPF is also given as negative 1/2 V. So, and then plus M1L squared over 12. And here we can also cancel out some of the L's. So if we cancel out, there's 3 terms and each one has an L, so we can cancel an L here, an L here, and this one has 2, so we're just going to cancel out the exponent. So now that we canceled all of those out, we're going to combine this term here with this term because they both have the same variables. And to do that, we're going to move this negative to the front, make it easier, so that becomes a positive. So now the term as a whole is negative, we can add it to this side. So when you add these two together, you'll have M2 1/3 V plus M2 1/3 times 1/2 V equals still on the other side, we still have M1L over 12 times, sorry, I forgot, I left out the angular velocity variable. This is the variable that we're looking for. So again, this, we can now combine all of this. We have M2 and V, they're both common in both terms, so we're just looking at the constants. So 1/3 plus 1/3 times 1/2 is 1/6. So 1/3 plus 1/6 is actually very big. If we do the math out, 1/3 plus 1/6, you want a common denominator, so you multiply this here. So it's going to be 2 over 6 plus 1 over 6 equals 3 over 6. So we have 3 over 6 can be simplified to 1/2 M2V. And we're going to divide by M1L over 12 so we can get this alone. So we divide by M1L, and the 12 down here will actually come up to multiply to the top. So 12 times 1/2 gives you 6 M2V over M1. And that is our final angular velocity for the rod. That is part B. And now moving on to part C. So part C is asking us to find the change in kinetic energy. So change in kinetic energy is given as kinetic energy final minus kinetic energy initial. And there's actually many components to the kinetic energy here because we're gonna have both linear and rotational. So first we're gonna find kinetic energy initial since that's gonna be the easiest to find. So kinetic energy initial is just and I'll write here that kinetic energy when we're looking at it linearly, it's 1/2 mv squared. But when we're looking at it kinetic energy rotational, it's 1/2 inertia angular velocity squared. So KE initial is just the point P mass moving. So we'll have 1/2 MP VP initial squared. And that is the only K initial because remember the rod has no energy because it hasn't moved yet. So we're looking at point P. So we have 1/2. We know that the mass of point P is M2. And we know that VP initial is just V. We square that. And that is going to be our KE initial. We'll leave that here while we look for KE finals. So KE final, we're going to look first at the KE final of the point P mass. Because again, that should be relatively simple. Since it's moving linearly, it's not the object that's rotating. So it's still going to be a linear kinetic energy. So 1/2 MP VP, instead of initial this time though, it's going to be its final velocity squared. So if you 1/2 M2, its final velocity was negative V over 2, square that, we'll have 1/2 M2, negative V squared is V, negative V squared is just V squared, 2 squared is 4, and if we multiply the 1/2 and the 1/4 here, we'll have 1/8 M2V squared. And that is the kinetic energy final of the point P mass. And then now we're going to look for the kinetic energy of the point of the rod. But since the rod has both a linear and rotational energy, we're going to break it into 2 separate calculations. So that is a horrible bracket, whatever. So KE rod final. There's going to be a rotational, so we'll do rotation. We'll do rotational first. Actually, I'll do linear since we've been doing linear up here. So I'll do kinetic energy final of the rod, and this is linear. So it's still going to be using the 1/2 MP squared. So that'll be 1/2 MR VR final squared, and we'll break it down. 1/2, we know that MR is M1, and we actually found VR final in part A. We found it to be, if you want to see, we found it to be, this is VR final here. So that's going to be 3M2V over 2M1. And that is our V final, and we're going to square that. So we're going to break it down further. We have 1/2 M1, and 3 squared is 9. That's M2 squared. V squared is V squared. And then 2 squared is 4. And then that's an M1 squared. There's a couple of things we can cross out here. We can cross out an M1, one of the M1s down here. We can cross out this M1 completely. And so we're left with 1/2 times 9 over 4. So 1/2 times 9 over 4 will give you 9 over 8. And then we still have all this up here, which is M2 squared times V squared. And at the bottom, we only crossed out one of the M1s, so we're still going to have an M1. And that's the kinetic energy linear of the rod at its final, at the final. So that is another term. And the final term is kinetic energy final of the rod rotational. And rotational, we know, I set up here is 1/2 inertia times, angular velocity squared. So 1/2 inertia of the rod times the angular velocity of the rod final squared. Break it down. 1/2 inertia of the rod. We know again, of course, to be we're gonna write it's m1l squared over 12, but we're gonna write the 12 out so that it's easier later when we simplify. So that leaves us m1l squared over 12, which is this here, and times the angular velocity final of the rod, which is what we just found in part B right here. So we can go ahead and plug that in. So that'll be 6m squared, or sorry, 6m2v over m1l. All of this is squared because here is squared. Let me check the numbers again. 6, yeah. Okay, so we have this, and we're going to break that down further, of course. We see a 1/2 times a 1 over 12. That's 1 over 24. And we see we can cancel. There's an m1 down here and an m1 up here. Go ahead and cancel it out. There's an l down here and 2 l's up here. We'll cancel the bottom one out, and we'll get rid of this exponent. So we are left with 124 times, there's a 6 in here, right? Actually, we can't cancel out yet. We have to actually distribute this exponent. So that's my mistake. I'll do that right now. That'll be m1l. This is, forget that we did this. So 6 squared is 36. m2 squared v squared over m1 squared times l2 squared. So actually, here we can still cancel out stuff. We can cancel out the l's. We can cancel out this m up here, leaving it us with just 1 m down there. And I'm gonna move this down here so we have more room. So we have 1 over 24 times this 36 here. So 36 over 24 is 3 over 2. We'll simplify that first. And then we have m2 squared v squared over this m1 here that's left over. So that is the final component for our kinetic energies. So looking here, back to the original equation that we wrote up top, it's going to be all the KE finals minus the KE initial. And the only, so 1, 2, 3 here, these are our KE finals. So we'll do 1/8 m2 v squared, first KE final, plus another KE final, which is 9 m2 squared v squared over 8 m1, plus another KE final, 3 m2 squared v squared over 2 m1, and we're subtracting the only KE initial that we have, which is 1/2 m2v squared. And we can see this actually works out quite nicely because we have a term here, 2 terms here with similar variables, and this term in the middle here has similar variables. So we can go ahead and combine those. 1/8 minus 1/2 is going to be -3 over 8 m2 v squared, the same variables, so we combine them. And these have the same variables too, with m2 squared v squared over m1. So 9 over 8 plus 3 over 2 is actually 21 over 8. And then we have the variables m2 squared v squared over m1. And that is our change in kinetic energy. And I'm just checking the question again. So yeah, that is all for FRQ number 4.